Greetings, everybody. So here I have a problem from our assignment that is a very important problem for me to do, and I have a little bit of reservation about it because I think it's a complicated problem. I think there's a lot of thoughts that have to happen in the right order that you have to understand in order to put everything together that's needed to understand how to solve this problem. So I guess what that translates into is it's a complicated problem, and this video might be longer than I like the average video to be, but that's calculus 2 for you, okay? So what it asks us from the beginning is if we can find a power series that is equivalent to this function, okay? And I think it's very hard to just jump into that and say, here's how to give the answer. So I'm going to walk you through all the thoughts and concepts and things we have to understand along the way to get there, okay? All right, so in this video, you will not see right off the bat how to solve it. I'm going to work my way up to it, but it's a video, so you could always skip around if you wanted to. So I want to give you this to start with. It's asking me for a series that represents this function. And how could that be? How could a series be equivalent or equal to a function at all? Well, look at it like this. Do you see this series right here? I'll claim to you that this series behaves like this function. Meaning when you put an x into this series and you calculate, and you put the same x into this function and you calculate, you get the same result. So a series can represent a function. Even though they look very different, they can mathematically work the same way. There might be a condition on it. Like I might have to say, well, sure, this series works like this function, but only if the x's you're working with are between -1 and 1. So that condition we call the interval of convergence. Okay, now how do I know that? It's well within your knowledge to understand why this is the case. That this series is equivalent to that function. Okay, here's how we know. This series is a geometric series. The first term is 1. R is -x squared. Okay, so we know what geometric series are, and we can identify this. Okay, so what does this geometric series converge to? Well, it converges to a1, the first term, divided by 1 minus r. So that's this. So that's how I know. That's how I know that this series behaves like this function. How do I get this interval of convergence? How do I say, well, the series and the function only are interchangeable if the x is between -1 and 1? Well, that's because for a geometric series to converge to a1 over 1 minus r, r has to be between -1 and 1, or you could say the absolute value of r has to be between -1 and 1. And in this case, if r is -x squared, that translates to the x itself being between -1 and 1. Okay, so that's how I know this series behaves like this function, number for number, as long as the x's are like that. Okay, now that's the first thought. So have that thought, make sure you understand that thought forwards and backwards. Now here's what we can do from here. If we have statements like that, where we're able to make a truthful claim that a series is equivalent to a function, this is a series, that's a function, then we can modify statements like that in two ways. I could take the derivative of all terms on both sides and get a new statement that's also true with the same interval of convergence, or I can integrate both sides, every term on both sides, and get also another statement that's true, same interval of convergence. So if I have some original statement relating a series and a function, I can modify that statement in two ways, and then I'll get a new series and a new function that's equivalent to it. So for example, if I take this original statement that we can agree about over here, okay, and I differentiate every term on both sides, then I'll get this. Okay, derivative of 1 is 0, derivative of -x squared is -2x, derivative of x to the fourth is 4x to the third, etc. Derivative of 1 over 1 plus x squared by the quotient rule is negative 2x over 1 plus x squared all squared. So then there's a new statement that's also true. This series is equivalent to that function for the same interval of convergence. Integrating both sides, look at that. Antiderivative of 1 is x, of negative x squared is negative x third over 3. And then the antiderivative of 1 over 1 plus x squared is tangent inverse of x. So then here's a new statement. This one's also true. This series behaves just like this function so long as the x is between negative 1 and 1. So to summarize that, if I know that some series is equal to some function, that's true, that I know that for whatever reason, these operations will produce new statements that are also true with the same interval of convergence. Okay? All right, so there's my second thought. Now we have to agree about this first thought, and we have to agree about this one too. Inside and out, forwards and backwards. Now, let's go backwards a little bit. I'll give you a question that's kind of like the one that we started with, where they're giving me a function and wanting to know a power series that represents it. Okay? So now I'm not doing that problem yet. I'm still working up to it. So I'll say, what do you think about this? Suppose I give you this function. Could you give me a power series that behaves like that function or is equivalent to that function? Could you do that? How would you come up with this series? Well, here's one way we can do it. We could look at this function and see, does it look like the kind of thing that's the sum of a geometric series? Well, what does the sum of a geometric series look like? A1 over 1 minus r. Does this look like that? See this function? Does it look like that? Well, okay, I guess like I could see negative 2 would be the first term. And then if I change that addition into a double negative right there, it could look like 1 minus r. So yeah, I mean, I guess if you give me that function, I can see that that does fit this mold right here, a1 over 1 minus r. And if that's true, I could say, well, look, this is the sum of a geometric series where the first term is negative 2 and r is negative x to the fourth. So yeah, if I get there, if I can see that pattern within this function, then yes, I can find that series. Can you write out a series that's geometric with a1 negative 2 r negative x to the fourth? If you can write that out, then yes, you can find the series that's equivalent to that function. And here it is. There's your geometric series. First term negative 2, r is negative x to the fourth. Okay, its interval of a convergence is for r, which is negative x to the fourth, between negative 1 and 1. At the end of the day, that means just x is between negative 1 and 1. Okay, so there. Now we got three things to agree about. One, that a series can be equivalent to a function. What the interval of convergence is, that we could take some statement like that, differentiate it, integrate it, get new statements. And then if I have a function and I want to find a series, one way to do that is to see if that function looks like the sum of a geometric series. Okay, now that's what we got to agree about to answer this question. So here's the question that's given in my math lab. Okay, so I know you can read it over here. I'm going to summarize it my own way. All right, so it says, can you find a series that's equivalent to this function? Now, based on how we did this problem right here, where I'm asking the question the same way, can we find a series equivalent to this function? I said, well, look, does this function look like it's the sum of a geometric series? Does it look like it's that kind of formula? Does it have that pattern? And in this case, I don't see that. Okay, it doesn't look like it can be modified in any way to get to be a1 over 1 minus r. I'm not saying that like maybe some genius can figure that out, but it doesn't look like that to me. Okay, so what else could we do? All right, if we just can't seem to figure this one out the way that we did this one, what else can we do? Well, remember when I said back here that if we have some original statement, and we know that's true, then taking the derivative of it or integral of it gets you new statements that are true. Maybe it's through that we can figure this one out. So here's what I'd like to see. Is the derivative or antiderivative of that something like the geometric series sum? Okay? Because if I can figure out that it is through that method, then I can go back to doing this or this to some statement that I already have. Okay, so let's see. What if you take the derivative of this? What do you get? You get that by using the quotient rule. That definitely does not look like the sum of a geometric series. So this must not be the way to go. What about the antiderivative? Okay, well, so this antiderivative can be done by u substitution, and you get that. And do you see that? That does look like the sum of a geometric series. The first term -2 and r negative x to the 4th. So yes, okay. So now I've got it. Okay, I've got a way that I think I can bring this about. Okay, now what's left for you to do is to figure out how you get some statement and use the derivative or integral to get something that applies to this. Okay, so here's how we do it. Let's write down a statement about -2/1 plus x to the 4th, which is the sum of a geometric series with the first term -2 r negative x to the 4th, which you see right here. Okay, now what do I do to that statement to make this show up? Well, okay, if integrating this got me there, and now I've written a statement like that, then differentiating it will get me back. Okay, so write down our statement involving this function, all based on it being a geometric series. Take the derivative term by term, both sides. Derivative of -2 is nothing. Derivative of 2x to the 4th is 8x to the 3rd. Derivative of 2x to the 8th is -16x to the 7th, and so on. And then the derivative of -2/1 plus x to the 4th is 8x to the 3rd, 1 plus x to the 4th squared. So now I have it. Now I wanted to begin with. The question was, what series is equivalent to this function? And now I have it. Okay? I had to do it in a very roundabout way. I had to think of some other series and function combination that, if I took the derivative of it, got me the one I wanted. So it does seem very roundabout, but that's how we would do it in this case. All right, so there's your answer. Like this right here, you see this? This series right here, that would be the answer to this question. Another wrinkle in this problem, though, is that all the answers are given in summation notation. So I would have to figure out which one of these gives me what I just got over there. And it's this one right here, okay? Which maybe take a little trial and error, but it wouldn't take you that hard to figure out which one of these summation notation formulas is going to give you this 8x to the 3rd minus 16x to the 7th plus 24x to the 11th minus, and so on. Okay, so that's how we'll get this one. We'll look among our options and select the one that works. Okay, about the interval of convergence, this last part, that's -1 to 1, and the reason for that is, if we go back to where we started, that what we were working with, that we modified right here to produce our answer, was a geometric series in the first place, whose interval of convergence was -1 to 1. Okay, so that's what this modified statement inherits the same interval of convergence. All right, so that's how it works. I told you it'd be a big problem, and I'm hoping with the first watch at the video you might see that, like, oh, I think I kind of get that, but it's something that's going to take some time to sink in, and I would think that's reasonable. That you would go through slide by slide, make sure you can agree with every premise in every slide working your way through until like it becomes natural to connect it all together. And of course, you get to try it out yourself by finding a similar problem in my math lab.